Hey kids, we are back, and today we're doing a little summary of systems of equations and inequalities, chapter 6. And well, I guess technically it's still spring, so I'm not doing a summary, I'm doing a springery. Well, anyway, here we go. Solving a system of equations is, remember, asking you, are there any points that these equations have in common? And I say that because you'll learn more and more complicated forms of systems of equations down the road with parabolas and other kinds of crazy graphs, and that's really always the goal. Do they have any points in common? When you're talking about lines, which these are, then you're really just talking about graphing the two lines and seeing where they intersect. All right, so for me, I like to graph lines by putting them in slope-intercept form. You can do it by finding intercepts and things like that also. So let's just practice here getting these into slope-intercept form though. That means to isolate y, make it y equals mx plus b. So this first equation right here, I'll use red for this just to keep them kind of straight. I want to subtract x from each side. When you subtract x, you'll be left with negative y equals, and then you'll have negative x minus 1 on the right side, and then there's a negative 1 out in front, so I want to divide everything by negative 1. I need it to be just y equals, right? Got to be completely isolated. So y equals positive x, and negative x divided by negative 1 is positive 1. So there is your equation in slope-intercept form, and so now I'm going to graph that. The y-intercept is 1. That's where I'm going to start on the y-axis. Put a dot at 1. And the slope is 1, right? When there's that unwritten coefficient, that's a 1. So from this point, go up 1 and to the right 1. Put a dot. Up 1 to the right 1. Up 1 to the right 1. And if you remember with systems of equations, since you're looking for where two lines are intersecting, you really want to be pretty accurate with your graph. So that's why I'm doing a little overkill here. I'm doing all these points. So not only up and to the right, but down and to the left one, down 1 to the left one, down 1 to the left one. And I'm using a ruler to draw it. So I want to make sure I'm nice and straight there, passing through all these points. I think I got a little off there, but there we go. So there's that line, very nice. And now let's graph this line. And to get this in slope-intercept form, I'm going to subtract 6x, right? I'm going to move those x's to the other side first. And so I will have 4y equals negative 6x plus 24. And I'm going to divide both sides by 4. Divide by 4, divide by 4, divide by 4. And we are left with y equals negative 3 halves x, because negative 6 divided by 4 is negative, and 6/4 reduced to 3 halves. Positive 24 divided by positive 4 is positive 6. So we have y equals negative 3 halves x plus 6. So I'm going to start at 6 on the y-axis, and then I'm going to go down 3 and to the right 2. Down 3 and to the right 2. And right there is really, boom, I know I'm right on the other line. That's the solution I'm looking for. If you want to do one more point just to draw a good line. But the solution to it, what you're looking for, is where do these graphs intersect, and that would be right there. And so my actual solution is that set of coordinates. So we want to list it as an ordered pair, not an ordered apple. 2, 3, that is that point. 2, 3 is your solution to the whole thing. And just so you know, I mentioned how you could do this by graphing this by intercepts instead of putting it in slope-intercept form. And just in case you remembered doing that and you liked it that way, the y-intercept for this graph would be putting 0 in for x, meaning that drops out and you get y equals 6. The x-intercept would be putting 0 in for y, so that part drops out, and then you have 6x equals 24, so x equals 4. So you could have done it that way, 6, 4, boom, and connected them. I like to have slope-intercept form because it gives you a lot of points, by using that slope, and sometimes you need to be really careful. So that's just what I prefer, but in case you were, thinking back to that. But overall, hopefully not too bad, right? Now, if you'll remember, graphing's great, but two lines don't always intersect at a perfect point. Sometimes they intersect at fractional values, and then your graph is not so helpful. Or sometimes you don't always have graph paper. So we needed some algebraic ways to do it, and one way was by substitution. And the goal with substitution was to change one equation into, instead of having two variables, into having one variable. And that was helpful if you had one variable that was isolated or easy to isolate. And if you'll notice right here, we have x is all by itself. X is equal to negative 4y plus 5. And here's when substitution is great. X is equal to this. So that means I can go into the other equation, and where I see x, that variable that's isolated, which is right there, I could take that x out and replace it with this. Since x is equal to negative 4y plus 5, I'm going to plug it in there just as if it was a number, but it's a whole algebraic expression. So this new equation I'll have will be 3, and in place of x, and then plus 6y equals 6, the whole first equation, but in place of x, I'm putting this expression of negative 4y plus 5. And so maybe it had been a while since you've done this, but everybody was pretty good at this back in the day, so it's a good time to review this. These are big on SATs, and they're very doable. So distribute, and now you'll have negative 12y plus 15 plus 6y is equal to 6. Combine your like terms here, negative 12y plus 6y. They're on the same side of the equation, right? So we just combine. So negative 6y plus 15 is 6. Subtract 15 from each side, right? When we move to the other side of the equation, that's where we do the opposite. We are left with negative 6y equals negative 9. And we're going to divide by negative 6, and you can see we're going to get a fractional answer. So y equals negative divided by negative is positive. 9/6 reduces to 3 halves. And you could use a decimal for that, because that would be 1.5 on, exactly. You wouldn't have to round. So if you'd rather use 1.5, be my guest. But you still need to find the other variable value. So I've got y, now I need x. So you plug it back into either equation, but the easiest one is the one where that variable was already isolated, this one. So if I go back here now, x is equal to negative 4 times y plus 5, and in place of y, I'm going to put the value I just found. 3 halves, distribute, solve. Negative 4 times 3 halves, right? Negative 4 times 3 is negative 12. Negative 12 divided by 2 is negative 6 plus 5. That's why I love fractions. Negative 6 plus 5 is negative 1. And there are your answers. If you want to express it as an ordered pair, I think that's always nice, because that reminds you that what you just found is where those two graphs would intersect if you were to graph them. But there you go. Okay, substitution. Pretty cool, right? But remember, the key to substitution was having a variable that was isolated, or one that was easy to isolate to start off, so that you could just plug it into the other equation. But if you look at this kind, you see that neither variable is isolated, and they wouldn't really be that easy to isolate. You'd have to, move some things around, divide, and you'll be left with some fractions. So it will still work, but it might not be the nicest way. And that's when we use this method, elimination. And really, of all the methods, this is probably the best method, because it kind of works no matter what form you're dealing with. But the goal with elimination is have them lined up this way. X's over x's, y's over y's, constants over constants. And you want to make opposites. You want to make two values that will cancel each other out. 5 and negative 5, 6 and negative 6, 7 and negative 7. And you'll often do this by multiplying each equation by something. So you can do whatever you want. So for example, I could, if I want to try to make my x's be opposites, this is 3x and 4x, I could multiply this one by, say, positive 4, and that will make 12x, and then I would want this one to be negative 12x, so they'll cancel out. So I'll multiply this one by negative 3. And you know, it didn't have to be the combination. You could easily have multiplied this one by negative 4 and this one by positive 3. Or you could have focused on trying to cancel the y's and multiplied this one by positive 11 and this one by negative 7. As long as you make opposites with one of the variables, there's more than one way to go through these. So it didn't have to be this exact set of steps. But we do that if you multiply. Just remember, you got to multiply that entire equation by something, right? The iron law of algebra. Do it to one thing, do it to all of it. So that first equation is going to become 12x plus 28y when I do 4 times 7y. And 4 times 1, don't forget the constants need to be multiplied too, 4. Negative 3 times this entire second equation, negative 12x, there's your opposites that you wanted. Negative 3 times positive 11y is negative 33y, and negative 3 times 8 is negative 24. Once you've got your opposites, this is where we combine the equations into one equation. And if they're opposites, they should cancel out. 12x minus 12x cancels. 28y minus 33y, that's negative 5y when you combine them. Or if you want to say I'm adding them together, whatever. And 4 minus 24. 4 and negative 24 combined to give you negative 20. And you see there's what you wanted. You've got it down to a single equation with only one variable, and it's very easy to solve. Divide by negative 5, divide by negative 5. Y is positive 4. And now that you've got y, plug it into any one of these equations for y and solve for x. It shouldn't matter because they should all give you the same answer. I like to go into the original ones because the numbers are a little smaller, but which one, it's totally up to you. So I'll go into the first one, why not? So 3x plus 7 and y is 4. And that becomes 3x plus 28 equals 1. Subtract 28 from each side. 3x is negative 27. Divide by 3, divide by 3. X is equal to negative 9. And so our ordered pair is negative 9 comma 4, right? Always alphabetical order, x before y. And there you go. That's where those two lines would intersect. And you could check it by graphing them and seeing that they intersect, or doing it by substitution and getting the same answer. A lot of ways to check yourself with this. Or even taking this 4 and plugging it into the other equation and making sure you still get negative 9. That is also a good way to check. But all right, so that's it for solving systems of equations, the 3 different methods: graphing, substitution, elimination. And now let's talk about the difference with a system of inequalities. Inequalities, remember, are not about equaling particular values. They're about boundaries, less than, greater than. So a system of inequalities was saying, you're going to shade and represent a set of all points that make both of these inequalities true. So you might recall that graphing linear inequalities, there's 2 things to concern yourself with. One, what type of line are you going to graph that with? A dashed or a solid line? And because it's just less than, not less than or equal to, and not greater than or equal to, there's no equal, that means you're going to use a dashed line, right? Okay, so I'm going to graph this line. I'm going to imagine it says, y equals negative 2/3 x, and graph it with a dashed line. So that would be, it's already in slope-intercept form. The y-intercept is 0 because there's no constant on the end. And the slope is negative 2/3. So down 2 to the right 3, down 2 to the right 3, or up 2 to the left 3, up 2 to the left 3. I'm going to graph that with a dashed line. Dotted, if you prefer to call it that, whatever you want. Okay, And remember that the dashed part is telling you that no points that are on the line are part of the solution, because these points, any point that's on this line is where these two are equal. And since we're not including the equal, that's why we use an open line, which is what this is, like when you use an open circle doing simple inequalities. But what you've just done is drawn a fence, basically separating this into two sides of the fence. One side contains all the points that are true for this inequality, and one side contains all the points that are false for this inequality. There's two ways to tell which side is the shaded side, the true side, and that's by either testing a point, and as long as it's not on the fence you can test it, or if you just pay attention to the direction of the sign, that's really what it's all about too. That this would be y is less than this line. Y is less than. Well, where would y values be less than this line? Would be underneath the line, any point under. So this would be shaded below. And if I were only doing this line, that'd be done. But it's a system, so let's take a look at this. All right, now this one, it's definitely going to be a solid line. I can see that right now because it's, got the or equal to. But as far as the shade above or below, you can't make that determination because it's not in slope-intercept form. So let's put it in slope-intercept form, and that would mean subtracting 12x from each side. So we'll have negative 4y is less than or equal to negative 12x plus 16, and then divide everything by negative 4. And I will have y is, now here's something you might recall, if you divide by a negative or multiply by a negative with inequalities, you have to flip the sign. So if this is less than or equal to, and you divide by a negative, you got to flip the direction, and now it's y is greater than or equal to whatever you get, from that resulting step. So in this case, that will be positive 3x. Positive 16 divided by negative 4 is negative 4. So now you're looking at this line, and there it's a solid line as we already determined, but because the direction changed, it's saying y is greater than this. Well, where y value is going to be greater, that's going to be above, shade above that line. I prefer that method rather than the testing points. Testing points can get tedious to me, and I think it shows more of an understanding of inequalities to say, hey, I'm just graphing above or below because it's greater or less than, but that's me. So y-intercept, negative 4. Slope, positive 3, right? And that's positive 3 over 1 if you like to imagine that unwritten denominator. So that would be up 3 to the right 1, up 3 to the right 1, up 3 to the right 1, up 3 to the right 1. And right, you get a pretty steep line. It's going to be solid. Okay, so now the system part of it is shading the one region that satisfies both lines. So I'm looking for anything that is below the red. So that would be all of this, anything below the red but above the blue. So above the blue would be, if you have trouble visualizing, pick any point, and that would be go straight up. Here's a point on it, straight up. Here's a point straight up. Anything right here is above the blue. So I want above the blue and below the red. That's going to put you in this region right here. And so this whole region is your solution to that system of inequalities. And that means any point you pick from this region, if you plug that into both inequalities, you'll get a true statement for both. If I pick anything from one of these regions, it will not make both true. It might make one of them true or neither, but it won't make both, and that's what you're looking for visually. So all right, and there we go. That's a pretty good little review of those ideas. And if you have any trouble with the homework, just let me know, ask questions. Have a good day, kids.